Dear students, welcome to the third module of Carbon Compounds chapter. The objective of this module is it aims at defining and explaining with examples of heteroatom, functional groups and homologous series. Let us recollect the important points of our previous module. Carbon is a versatile element. It exhibits characteristics like catenation power, multiple bonds, tetravalency, as well as isomerism. The hydrocarbons can be saturated or unsaturated. There are certain steps to be followed while writing a line structure of a compound. The carbon chain can be a straight chain, branched, or an open chain. All types of carbon atoms, that is, let it be an open chain or a branched or a ring structure, they can be saturated or unsaturated. So children, so far we have seen carbon compounds made only of carbon and hydrogen. But more types of carbon compounds can be formed by bonding of carbon with other elements like halogens, oxygen, nitrogen and sulfur. The atoms of these elements substitute one or more hydrogen atoms in the hydrocarbon chain. Take for example, so this is methane. If you see, either one hydrogen atom or more than one can be substituted. So the atom which is substitute for hydrogen is referred to as a heteroatom. Here in this case it is chlorine. So the atom which is substitute for hydrogen in a carbon compound is known as a heteroatom. But if you see, sometimes the heteroatoms are not alone but groups of atoms. See, for example, here one hydrogen is replaced by groups of atoms. If you see, you can see one carbon atom, two oxygen atoms and one hydrogen atom is also present. So heteroatom may be single or in a group. So what is the importance of these heteroatoms? If you see, the compounds, when a heteroatom is added, they acquire specific chemical properties, okay, due to the heteroatom or a group of atoms. So the properties are irrespective of the length and nature of the carbon chain in that compound. So these heteroatoms or the group of atoms containing heteroatoms are called functional groups. Together they are called functional groups. So functional groups give specific properties to a carbon compound. If you see, not only those, even the carbon-carbon double and triple bonds are also functional groups as the compounds get specific chemical properties due to them. Now let us see some general functional groups. So if you see, every functional has a specific heteroatom. We will see one by one. The first one is a halogen. The halogen may be chlorine, bromine or iodine. So depending on the type of the halogen, the name can be indicated as chloro, bromo or iodo. So generally they are denoted with the letter X and specifically as Cl, Br and I. Their symbols you know that very well. And this is the structural formula, condensed, that is a simplified structural formula. So this column gives you an elaborate structural formula. We will see how they get applied with the carbon compound one by one. So alcohol, that is, in which if you see, there are 6 functional groups in which oxygen plays a major role apart from carbon and hydrogen. The first one is alcohol with one oxygen and one hydrogen, and aldehyde with carbon, oxygen and hydrogen. You can say how they are linked with each other. The next one is ketone, which contains only carbon and a double bond attachment with the oxygen atom. Then carboxylic acid, which contains one carbon, two oxygen atoms and a hydrogen. Then ether with only oxygen atom. Ester with carbon and two oxygen atoms. In all the 6, oxygen is the heteroatom. The next one, if you see, nitrogen being a heteroatom in a group called amines, where you can see it nitrogen with two hydrogen, that is NH2. If you see the free valency of the functional groups, that is the valency which is free with each functional group, is indicated by a short line. You can see some are having only one short line and some are having two. So depending upon the free valency, the short lines are indicated, and the functional group taking place of hydrogen is joined with the hydrocarbon with this valency only. So we will see, when we see with examples, I think you can understand better. We will see one by one. Before learning the functional groups, let us learn the name of the carbon compounds depending on the number of carbon atoms. See, I have given you two tables where the carbon skeleton extends from 1 carbon to 10 carbon. You have to note that I have given only the carbon skeleton, not the hydrogen. It doesn't mean that it is not there, it is there. But let us concentrate only on the carbon. First, if there is only one carbon present, the name starts with METH, meth, and as it is a saturated hydrocarbon, as we learned earlier, the name ends with ANE. Methane is a one carbon compound. If there are two carbon, then the name is ETHANE. ANE denotes that it is a saturated hydrocarbon, and ETH means there are two carbon atoms in that hydrocarbon. If there are three, it becomes prop, PROP, and ANE denotes the again the saturated carbon chain. And if it is 4 carbon, it is but, BUTANE, butane here. 5 carbon pent, 6 carbon hex, 7 carbon hept, 8 carbon oct, 9 carbon non, and 10 carbon dec. So this is important. Depending on the number of carbon atoms, the name changes. If you see this table, with the presence of double bond, you can see the A in the ANE getting replaced by E. That is, ethene means the presence of double bond. ETH represent that there are two carbon atoms, and E represent there is a double bond between these two carbon atoms. Now, accordingly, you can see with the presence of double and triple bond, whether it is replaced by E for double bond, or if it is triple bond, the A is replaced by Y. And depending on the number of carbon atom, you can see the name changes. So it is very important to remember at least this 10 names. So it will be easier to identify and name them. Let us see some examples of hydrocarbons with halogens as heteroatoms. As we have learned, halogens may be chlorine, bromine, or iodine. So they will have the name as chloro, bromo, or iodo depending on the halogen present. See the structure, first structure. How many carbon atoms are there? There are two carbon atoms. So if there are two carbon atoms and there is only single bond between them, it becomes ethane. And since there is a presence of one halogen, that is chlorine, the name is chloroethane. So this is a condensed formula, and we can see an elaborate structure. If you see, this is the structure of ethane. You can see CH3, single bond CH3. So here what happens? One hydrogen is replaced by this halogen chlorine, and now this became chloroethane. Second, if you see, the chlorine can be bromine also. Bromine is also one of the halogen. So it is possible that instead of chlorine, there may be bromine atom also. If it is bromine, the name changes as bromoethane, and we can see one hydrogen atom is being replaced by bromine. Then Let us substitute iodine. With iodine, the names becomes iodoethane and the hydrogen atom can be replaced with iodine. See, don't think that I have to replace only this hydrogen atom. You can replace any of the hydrogen atom present and the name will become same. Then the bromine can be attached with the front carbon atom also. Here we are attaching with the last carbon, but they can be present along with the first carbon also. Then also the name is bromoethane. When you learn about nomenclature, you can learn it in detail. And here I have replaced this hydrogen with bromine. Then you are seeing a different structure where bromine is attached to the second carbon atom. So to indicate the location in which the bromine is attached, I have here written as 2-bromopropane. Propane means a 3 carbon. ANE means that it is a saturated hydrocarbon. 2 indicates the place or the carbon with which the bromine group is attached. So this is the elaborate structure of 2-bromopropane. You can see the bromine being attached to the carbon and you can check that the tetravalency of carbon is satisfied with every carbon, which is very important in any hydrocarbon chain. Let us move to the next examples using alcohol and aldehyde. Both contain oxygen as a heteroatom and you can see there is a difference in structure between alcohol and aldehyde. Alcohol is indicated with OH and aldehyde with CHO. The first example I have given is ethanol. So ethane means there is a single bond between carbon. OL is the suffix or the end part of the name that is going to indicate the presence of alcohol heteroatoms. So here is an elaborate structure where you can see the first group CH3 group and then CH2 and then OH. This is how they are linked with each other. So this is the structure of ethanol. The next one with one more CH2, that is the chain becomes propanol. 3 carbon, it is a propanol. OL indicates the presence of alcohol. So this is an elaborate structure. Every time it is a must that you have to see that the tetravalency of carbon is satisfied. Then we will see the next structure, which is with the aldehyde hetero group. The difference you have to note here is the group itself is having a carbon atom, but our aim is to count the number of carbon atoms to name it. I have given here as propanol indicating the presence of 3 carbon atoms. You count whether it is there in the chain or it is present along with the heteroatom in the functional group. Irrespective of that, you have to calculate all the carbon atoms. So let me count the carbon atoms. I have 1, 2, 3. So the name will be propanol. Al indicates the presence of aldehyde functional group. So this is the elaborate structural formula. Count the number of carbon atoms 1, 2, 3. Even if it is present along with the functional group, you have to count this carbon also. It is must. Hence the name propanol. Let us see one more structure, butanol. So here there is 1, 2, 3, 4 carbon atom present. Al means the presence of aldehyde and here is the structure of butanol, 1, 2, 3, 4 carbon atom and this is the way of representing an aldehyde functional group. The next structure is 2-propanol. Here I have changed the position of the alcohol group. I have connected with the second carbon as we have seen in the previous slide. So I am attaching with first, second and third carbon. So second carbon is having the alcohol group. So I have indicated the position, and the number of carbon indicated by the name prop means that 3 carbon, and ANOL, A indicates that it is a saturated hydrocarbon, OL indicates the presence of alcohol group, and this is the structure of 2-propanol. You can count the number of carbon atom and you can check the tetravalency of the carbon atom. Now let us learn how ketone and carboxylic acid are represented. So ketone, the structure formula is C double bond O, and carboxylic acid will be C double bond O and OH. Let us see some examples. The first one is with the ketone C double bond O. You can see I have attached this ketone within 2 carbons. See, if you see the ketone structure, it has 2 valencies to be satisfied. So there is no way I can place it in either end of the carbon chain, but I have to place it only in the middle so that the valency of ketone can be satisfied. So now let us count the number of carbon atoms. I have 1, 2, 3 and 4. So it should be but. A represent as a saturated hydrocarbon, and the presence of a ketone functional group is represented by the name ending with ONE. So the name is pronounced as butanone to represent the position in which the functional group is present. Let us see the structure. So this is the elaborate structure where you can see very well the tetravalency of carbon being satisfied and the presence of functional group as well. So the next structure is with an acid. Here also you can see carbon being present along with the carboxylic acid functional group. So I have to take this carbon also into account. So it indicates the presence of 2 carbon atom, hence the name ethane. The functional group carboxylic acid is indicated by the name OIC acid at the end of the main name, that is ethanoic acid. The structure is CH3COOH. You can see the elaborate structure here. So CH3 is the methyl group and COOH is the functional group, that is carboxylic acid group. Due to the presence of 2 carbon atoms, the name contains ETH. The next one is propanoic acid. Again, it ends with OIC acid. Propan means that there are 3 carbon atoms. There are 1, 2 and 3. And here is the elaborate structure of propanoic acid. So this is how ketone and carboxylic acid are represented. We have seen one more example of ketone, that is 2-propanone. So 1, 2, 3 carbon atom, the name propan, ONE indicates the presence of ketone and 2 indicates the position in which the functional group is present, and this is the elaborate structure of propanone. Next comes ether and ester. So ether contains only oxygen as a heteroatom, where ester contains carbon and 2 oxygen atoms. So when we are, as we have seen in ketone, the same with ether, since oxygen needs 2 valency to be satisfied, it should be placed in the middle of the hydrocarbon. You can see I have given one methyl group CH3 and an oxygen. So this is the ether group, and then CH2 and CH3. So the name, if you see, it is ethyl methyl ether. If you see, whatever is there attached with the functional groups, that is in the right side of the functional groups, it will be represented first. The group together can be represented first. So it is an ethyl group. So ethyl, and then in the left is methyl. So it is methyl, and then the name ether representing the presence of the functional group ether. So this is how it is represented elaborately. Now with ester, it likewise like ether and ketone, this also will be occupying the middle of a carbon chain. So you can see the structure. So as the naming is similar to ether, here also it is, first you have to see the right side. After the functional group, it is 2 carbon, so it is ethyl. And why I have written ethane means that there is 1 carbon to the left and 1 carbon in the functional group. I should not leave this carbon at all. So it is ethyl ethanoate. OATE is the name change with the presence of ester functional group. So this is an elaborate structure. You can see the tetravalency of carbon, single valency of hydrogen and double valency of oxygen. Everything is being satisfied. It is always recommended to write the structure in this elaborate model so that we will not leave any mistakes. The last one is amine, the presence of nitrogen as a heteroatom. You can see the name, the first one, an amine group with a methyl group, and the name is methanamine. So to indicate the presence of amine group, we just attach the name amine itself with the main name. So this is the elaborate structure of methanamine CH3 and NH2. Then next one is propanamine. It means that presence of 3 carbon atoms, 1, 2 and 3, and amine represent the presence of amine group. So this is the elaborate structure of it. So hopefully you have understood how the functional groups are getting attached to the hydrocarbon and how they change their names as well. Now we will move on to the next topic of the chapter, that is homologous series. Given is a table of a homologous series starting from 1 carbon to 10 carbon. So what is a homologous series? It is a series of compounds formed by joining the same functional group. The functional group may be anything that we have seen previously, or even a double bond, single and triple bond, all are functional groups, in the place of a particular hydrogen atom having sequential increasing length. Sequential increasing means 1 carbon, then 2, 3 carbon, 4 carbon, like that. So this is called a homologous series. If you see their chemical properties, they are very much similar. There are different homologous series in according to the functional group. So like a homologous series of alcohols, aldehydes, carboxylic acid, etc. are present. All the members of homologous series are homologues of each other. If you see, they differ only with one extra methylene unit, that is CH2. You can very well note it down. The first and second differs by a extra 1 carbon atom, that is 1 CH. Here it is 1 CH2 extra, then 1 CH2 extra, like that. They increase with 1 methylene unit. And there is a raise in molecular mass of the members by 14 Dalton. How it is 14 Dalton? So if you see, they differ by 1 CH2 group. It means that 1 carbon with atomic mass of carbon is 12 and 2 hydrogen atom present, the sum becomes 14 Daltons. The homologous series has some special characteristics. While going from one member to the next in the homologous series, you will see an increase in one CH2 unit and the molecular mass increases by 14 Dalton, and you can see the number of carbon atoms increases by 1. The chemical properties of the members of homologous series shows similarity. All the members can be represented by the same general molecular formula. Let us see homologous series of alkanes first. If you see, the first one is methane with 1 carbon. The number of carbon atoms is 1. Number of CH2 units, that is CH2 with two valency. They should be attached to some other hydrocarbon. Here you can ask, there is no presence of CH2 but it is represented as 1. How? As you see, this CH4 can be written as CH2 with two single bond on the either side. So that is why it is represented as 1 here, and you can see each series is increasing with one CH2 unit, and that is why butane has 4 carbon atoms with 4 CH2 units, pentane has 5 carbon atom with 5 CH2 units, and hexane have 6 carbon atom with 6 CH2 units. You can see they behave as separate compounds. You can make out by the difference in their boiling point. The same way is the homologous series of alcohols. You can see the number of carbon atom 1 and number of CH2 units. You can see CH2 can have 2 single bond on the either side. So it is represented as 1. And likewise propanol will have 3 carbon atom, 3 CH2 units, and butanol will have 4 carbon atoms and 4 CH2 units. This molecular formula, they have counted all the carbon and hydrogen together and written like this, and this is the condensed, that is simplified structural formula. You all know how an elaborate structural formula can be written, and the boiling point represent they all behave as independent or separate compounds. Let us see one more homologous series of alkenes. Here there is a difference, you have to note it down. The first one is, if you see, even though there is a presence of 2CH2 here, the number of CH2 units represented is given as 0. Can you guess why? Because our condition is the CH2 unit should be represented with single bond on the either side, which is not possible here because both the CH2 units are connected via a double bond. So hence it is written as 0. But if you see the second case, it is possible to have one CH2 unit. Likewise, this CH3 can be represented as CH2 with a single bond on the either side. So the number of CH2 unit is written as 1 here. So you can guess the remaining, where one butene ENE represents the presence of double bond. So one butene will have 4 carbon atom and 2 CH2 units, where one pentene will have 5 carbon atoms and 3 CH2 units. We have learned a lot in this module, so let us summarize whatever we have learned. First, the atom of the element which is substituted for a hydrogen atom in a hydrocarbon is referred to as heteroatom. So these heteroatoms can be single or group of heteroatoms. So these are called functional groups. The carbon-carbon double and triple bond are also recognized as functional groups as they change the chemical properties of the hydrocarbons. So we have seen many functional groups ranging from halogens to oxygen heteroatom and nitrogen as well. And the series of compounds formed by joining the same functional group in place of a particular hydrogen atom is called a homologous series. It increases with sequential carbon atom, that is 1, 2, 3 carbon atoms like that. And the chemical properties of the members of a homologous series shows similarity. All the members of the homologous series can be represented by the same general molecular formula. So that's all of this module. There is so much we will learn about this chapter, especially about nomenclature in the coming module. So thank you so much.